All right, let's get back into it. Starting on functions. I apologize in advance if I cough in the microphone. I'm going to try not to do that. Even though I got this cough going, I'm going to try to mute myself. Practice some broadcasting skills here. This is a high quality stream, so I want to put some effort into it. All right, high production value. All right, so functions. In C, a function is equivalent to a subroutine or function in Fortran, or procedure or function in Pascal. So subroutines and procedures are terms for basically functions that don't return. That's my understanding. I've only ran across them in Perl. I think I was writing like Perl 3 or Perl 4 when I was younger. And they had subroutines and procedure. I don't know if they call them procedures. But there's other languages that refer to them as procedures, like Pascal, I guess. It'd be nice to go back and learn some of those older languages at some point in my life. But yeah, a function provides a convenient way to encapsulate some computation, which can then be used without worrying about its implementation. With properly defined functions, it is possible to ignore how a job is done. Knowing what is done is sufficient. C makes the use of functions easy, convenient, and efficient. You will often see a short function defined and called only once, just because it clarifies some piece of code. Yeah, I agree. It's a good thing to do. Let me get my little lamp here going. So far we've used only functions like printf, getchar, and putchar that have been provided for us. Now it's time for us to write a few of our own. Since C has no exponential operator like the star of Fortran, let us illustrate the mechanics of function definition by writing a function power mn to raise an integer m to a positive integer power n. That is, the value power 5 is 32. This function is not a practical exponentiation routine since it handles only positive powers of small integers, but it's good enough for illustration. The standard library contains a function pow xy that computes x to the y. Here is the function power in a main program to exercise it, so you can see the whole structure at once. So you do a for declaration, int power m and n are integers. Then we have a main that we just go through the first 10 integers, or 0 to 9, I should say. And then we take 2 to the power of that integer, and then -3 to the power of the integer. Let's go back here. And since -3, if it's an even power, then it'll be a positive integer. All right, here's an implementation. Power, So we have our base and our exponent. P we set to 1 for I, and I is less than n, less than or equal to n. Equal is important because we're starting at 1. I plus plus. Usually you start at 0 and then you go up to less than n. And then plus plus I, and then we just multiply P times itself. Or sorry, P times base that many times. Make sense? Yep. A function definition has this form. Yep. Function definitions can appear in any order. And in one source file or several, although no function can be split between files, if the source program appears in several files, you may have to say more to compile and load it than if it all appears in one. But that is an operating system matter, not a language attribute. For the moment, we will assume that both functions are in the same file, so whatever you have to learn about running C programs will still work. The function power is called twice by main in the line printf, and they give it twice here. Each call passes 2 arguments to power. With each time returns an integer to be formatted and printed. In an expression, power to I is an integer just as 2 and I are. Not all functions produce an integer value. We'll take this up in chapter 4. The first line of power itself, int base, int n, declares the parameter types and names, and the type of the result that the function returns. The names used by power for its parameters are local to power and are not visible to any other function. Other routines can use the same names without conflict. It's also true of variables I and P. The I in power is unrelated to the I in main. We will generally use parameter for a variable name in the parenthesized list of a function definition. An argument for the value used in a call of a function. The terms formal argument or actual argument are sometimes used for the same distinction. The value that power computes is returned to main by the return statement, and the expression may follow return. A function need not return a value. A return statement with no expression causes control. Wait a minute. A return statement with no expression causes control, but no useful value to be returned to the caller, as does falling off the end of a function by reaching the terminating right brace. And the calling function can ignore a value returned by a function. We have noticed that there is a return statement at the end of main. Since main is a function like any other, it may return a value to its caller, which is in effect the environment in which the program was executed. Typically, a return value of 0 implies normal termination. Non-zero value signals unusual or erroneous termination conditions. In the interest of simplicity, we have omitted return statements from our main functions up to this point, but we will include them hereafter. It is a reminder that programs should return status to their environment. The declaration int power, int n, and int n just before main says that power is a function that expects 2 arguments and returns an int. This declaration, which is called function prototype, has to agree with the definition and use of power. It is an error if the definition of the function or the use of it do not agree with its prototype. Parameter names need not agree. Indeed, parameter names are optional in a function prototype. So for the prototype, you could have written int power, int int. It's kind of like in Go. You can do the same thing, not with for declarations, but with interface methods. Well-chosen names are good documentation, however, so we will often use them. A note of history: the biggest change between ANSI C and early versions is how functions are declared and defined. In the original definition of C, the power function would have been written like this. I love this. Because I've never ran across this before. I'm curious if this would even work in a modern compiler. So you say power base n. So you pass in arguments, but you don't declare their types. And then in between the parenthesized arguments, you then declare the types to be local. And then you also have declaration inside the code block. I was under the impression all the declarations were between the function name, its parameters, and the code block. But it looks like you can also have them up here. Very, very interesting. Let's do test old style func. .c. And we're going to call this thing power base n. And then we're going to say, how do we declare that it returns an integer though? I guess it does type inference on p. That's pretty crazy if it does that. Int base n. And then in here, we'll have int I p. P is equal to 1 for I is equal to 1, I is less than or equal to n plus I. And then down here we say p is equal to p times base. And then return p. Yeah, it doesn't like that. And then this can be they don't have main. Let's just delete all this and say return 0. I wonder if I can get this thing maybe like that. A parameter list without types is only allowed in a function definition. That is a function definition. Okay, I'll keep the semicolon there. And then I'm going to Emacs this. And I'm just going to delete this. Oops. So, lost my focus there. File save. And then file quit. Okay. Cat out test old. That's SAI. Is it possible to compile old style function functions in C like this? And I'll just pipe that into word count, not word count, Wayland copy. Bam. I'm curious if it's even possible nowadays, or if the compilers are just completely moved on from it. Well, let's try passing into GCC. Test old. Doesn't like it. It would say standard is GNU 89. Can you imagine still being on this version of C? It works. That's good. That's good stuff right there. Let's actually make sure it runs. Test old style func. And I'm just going to do a... okay, we'll include standard IO. Oh, sorry. Include standard IO dot h. Down here, printf, and we'll give it percent. We'll just say percent %d colon percent %d new line, and we'll say we'll do it like this. Pow of %d that is equal to that. Then here we can say what? 2 to the power of 10, and then power of 210, and then down here I should probably change this to be power. I wonder if I can compile it with the thing messed up on a single line that way. Yeah. It works. Kind of crazy. Kind of crazy. So I'm gonna remove a.out and then vim up the makefile. I'm just gonna pull this thing down here. I need to delete this thing. I saw this earlier. I forgot to delete it. So all C programs get compiled into this stuff, but I'm gonna have my own thing that's called build test old style func. Is that what it's called? Old style func. And it's gonna take in test old style func C. And this guy, definitely not gonna use XCC. GCC, target we can do away with, all this we can do away with, and we just say output to the target, that file, but we have to give it the standard equals GNU 89. Make all, make clean, make, okay, and then build test old. There we go. I'm going to open up Emacs on test old again because I want to have it look somewhat like the old K&R style. There we go. And now you can say save, quit, cat. There we go. Make. There we go. Okay. That was just a bit of a tangent because I wanted to explore the syntax a little bit more. Because I've only seen it once before, and it was AI spitting it out to me. I've never seen it anywhere else, so I just wanted to explore that a little bit. The parameters are named between the parentheses, and their types are declared before the opening left brace. Undeclared parameters are taken as int. The body of the function is the same as before. The declaration of power at the beginning of the program would have looked like this: int power. No parameter list is permitted, so the compiler could not readily check that power was being called correctly. Indeed, since the default power would have been assumed to return an int, the entire declaration might well have been omitted. The new syntax of function prototypes makes it much easier for a compiler to detect errors in the number of arguments or their types. The old style of declaration and definition still works in ANSI C, at least for a transition period, but we strongly recommend that you use the new form when you have a compiler that supports it. Exercise 115, rewrite the temperature conversion program section 1.2 to use a function for conversion. I don't want to do that. Arguments called by value. One aspect of C functions may be unfamiliar to programmers who are used to some other languages, particularly Fortran. In C, all function arguments are passed by value. Thank you. Even if it's a pointer, the pointer is getting copied. This means that the called function is given the values of the arguments in temporary variables rather than the originals. This leads to some different properties than are seen with call by reference languages like Fortran or with var parameters in Pascal. in which the called routine has access to the original argument, not a local copy. The main distinction is that in C, the called function cannot directly alter the variable in the calling function. It can only alter its private temporary copy. Call by value is an asset, however, not a liability. It usually leads to more compact programs with fewer extraneous variables because parameters can be treated as conveniently initialized local variables in the call routine. For example, here's a version of the power that makes use of this property. I'm not sure what property they're talking about. It usually leads to more compact programs because parameters can be treated as conveniently initialized local variables. Okay. The parameter n is used as a temporary variable. Oh, the decrement on the n, I get it. And it's counted down a for loop that runs backwards until it becomes 0. There is no longer a need for the variable I. Whatever is done to n inside power has no effect on the argument that power was originally called with. When necessary, it is possible to arrange for a function to modify a variable. In a calling routine, the caller must provide the address for the variable to be set, technically a pointer to the variable. And the called function must declare the parameter to be a pointer and access the variable indirectly through it. We will cover pointers in Chapter 5. The story is different for arrays. When the name of an array is used as an argument, the value passed to the function is the location or address of the beginning of the array. There is no copying of array elements. By subscripting its value, the function can access and alter any element of the array. This is the topic of the next section. Character arrays. The most common type of array, did I not advance here? There we go. Character arrays. The most common type of array in C is an array of characters. To illustrate the use of character arrays and functions to manipulate them, let's write a program that reads a set of text lines and prints the longest. That line is simple enough. While there is another line, if it's longer than the previous longest, save it and save its length. Print the longest line. Okay. This outline makes it clear that the program divides naturally into pieces. One piece gets a new line, the other tests it, another saves it, and the rest controls the process. Since things divide so nicely, it would be well to write them in that way too. Accordingly, let us first write a separate function getLine to fetch the next line of input. We would try to make the function useful in other contexts. At the minimum, getLine has to return a signal about possible end of file. A more useful design would be to return the length of the line, or 0 if end of file is encountered. 0 is an acceptable end of file return because it is never a valid line length. Every text line that has at least one character. That isn't true. Even a line containing only a new line has length 1. I wouldn't consider that a line though, right? It's like a delimiter, it's not part of the line. When we find a line that is longer than the previous longest line, it must be saved somewhere. This suggests a second function copy to copy the new line to a safe place. Finally, we need the main program to control getLine and copy. Here's the result. Okay. Give me 1 second, I'll blow my nose. Sorry, I think my headset was dead there. Well, hopefully I wasn't muted for too long. So we got 2 for declarations for get, line, and copy. They take some arrays, character arrays. So we go into our main. We declare some variables I don't care about. I guess the line up to max line and longest max line are important. We call get line. We give it the line itself and the max line size. Get line uses get car, which is kind of like, okay, got C libraries for this. Oh. Give me 1 second, someone's at my door. All right, so we call get line. We're reading into the line buffer, and then if the length of that line is greater than the max, then we record it as the new max and we copy it into the longest buffer. And then if max is greater than 0, which means there was at least 1 line, then we print out whatever the longest line was. And then the get line takes in a character array. This is interesting because I normally take in a char star and a length, which I guess they're taking in a length. But instead of saying char star, they say character array here as an argument. So I is equal to 0, I is less than limit -1 because you have to null terminate it. And then we get our character. If it's not equal to EOF, then we assign it into the location. And then we also have to make sure it's not equal to new line. And then the last thing was new line. Then we assign it into SI and we increment I again. Wait a minute, what the hell is going on here? Why did they have to complicate this? So we call K&R C. We say, okay, it needs to not be equal to EOF. Fine. And it needs to not equal new line. So it can't be the new line character and it can't be the end of file character. Signal. I guess signals are the character that's assigned to the EOF symbol. And then once we exit the loop, we say if the character was the new line character, then we assign it and we increment. Why couldn't we have done that as part of the main loop? You're not doing anything special there. Let's see. Yeah, I don't understand why they broke that out. And at the end, they just assign in the null byte, which is what I was anticipating. And then copying is just going over the entire array until you hit a null byte. What's interesting is you have from to. So this is like trusting that there's a null byte in the array and not passing in an explicit limit on it. So you could literally copy like the entire memory of the program and everything. This is like, that's not a good function there, not a safe function. I'm curious why they did this. Let's ask AI. Maybe it knows. In K&R C, they have a code example. Int getLine char s int lim, and then in here there's a code block. Int ci. And then we say for, and then we say I is equal to 0. I wish I could select this, I can't though. I is less than limit minus 1, and C is equal to get char, and then all that is not equal to EOF, and C is not equal to new line and plus plus I. Then down here, S sub I is equal to C. If C is equal to new line, then we S sub I C plus plus I. And down here, treat S sub I is equal to /0, return I. Why is /new line character treated specially? Wouldn't and skipped see what AI says. Oh, okay. I'm assuming EOF is... Okay, I got it. That's why they call it out. I was just assuming that EOF would be the signal that the line is done reading. but that's end of file, not end of line. That makes sense. Okay. Let's move on. Okay, next page. The function getLine and copy are declared at the beginning of the program, which we assume is contained in one file. Main and getLine communicate through a pair of arguments. In the return value in getLine, the arguments are declared by the line int getLine char array int limit, which specifies that the first argument s is an array and the second limit is an integer. The purpose of supplying the size of an array in the declaration is to set aside storage. The length of the array s is not necessary in getLine, since its size is set in main. Wait a minute. The length of the array s is not necessary in getLine. Huh? The hell are you talking about? Of course it's necessary. The length of the array s is not necessary in getLine since its size is set in main. getLine uses return to send a value back to the caller, just as the function power did. This line also declares that getLine returns an int. Since int is the default return type, it could be omitted. I'm not sure. The phrasing of that paragraph seems kind of weird. Some functions return a useful value. Others, like copy, are used only for their effect and return no value. The return type of copy is void, which states explicitly that no value is returned. getLine puts the character null, the null character, whose value is 0, at the end of the array it is creating to mark the end of a string of characters. This convention is also used by the C language when the string constant like hello/n appears in a C program. It is stored in an array of characters containing the characters of the string and terminated with a null to mark the end. This %s format specification in printf expects the corresponding argument to be a string represented in this form. Copy also relies on the fact that its input argument is terminated by 0 and it copies this character input to the output argument. All this implies that 0 is not part of normal text. It's worth mentioning in passing that even a program as small as this one presents some sticky design problems. For example, what should main do if it encounters a line which is bigger than its limit? getLine works safely in that it stops collecting when the array is full, even if no new line has been seen. By testing the length of the last character returned, main can determine whether the line was too long and then cope as it wishes. In the interest of brevity, we have ignored the issue. There is no way for a user of getLine to know in advance how long an input line might be, so getLine checks for overflow. On the other hand, the user of copy already knows or can find out how big the strings are, so we have chosen not to add error checking to it. Exercise 116 provides the main routine of the longest line program so it will correctly print the length of arbitrary long lines as much as possible of the text. The way that they phrase that, they're just going to have you, or they would want you to just throw away the text as you see it and just keep a running count of the line size. I'm not really interested in implementing that. It's not too difficult to implement, but let's move on to the next page. We have other exercises. Write a program to print all input lines that are longer than 80 characters. It's just a small filter, and then the line length, it'd have to be longer than 80 but shorter than the max length. What I want them to do is I want him to ask you to implement table doubling and some type of like copying and updating of the array and heap allocation. But he's not going to ask for that. Write a program to remove trailing blanks and tabs from each line of input and to delete entirely blank lines. So you're not going to know if they're trailing or not until you get to the end of the file. So basically what you do to implement this is you would be at the end of the file, at the end of get line, and then you just walk from the end back. And when you hit a what they call it, empty trailing blanks or whatever, you would then move forward one again and put your null byte there. Write a function reverse that reverses the character string s. Use it to write a program that reverses its input a line at a time. So for that, you just have two indices, and you go from the ends to the middle, swapping bytes. And you can do that with an XOR swap or with a temporary variable. Temporary variable is probably more straightforward and probably even performs better. All right, external variables and scope. How many more pages we got here? Hey, we're almost done with this chapter. The variables in main, such as line, longest, etc., are private or local to main because they are declared within main. No other function can have direct access to them. The same is true of the variables in other functions. For example, the variable I in getLine is unrelated to the I in copy. Each local variable in a function comes into existence only when the function is called. Each local variable in a function comes into existence when, and disappears when the function exits because it's on the stack. Obviously, this is why such variables are usually known as automatic variables. This is like a name that I've ran across a few times now. I've always just called them stack locals, but I guess people refer to them as automatic variables. Following terminology in other languages, we will use the term automatic henceforth to refer to these local variables. Chapter 4 discusses a static storage class in which local variables do retain their values between calls. Because automatic variables do come and go with function invocation, they do not retain their values from one call to the next and must be explicitly set upon each entry. If they are not set, they will contain garbage. As an alternative to automatic variables, it is possible to define variables that are external to all functions, that is, variables that can be accessed by name by any function. This mechanism is rather like Fortran common or Pascal variables declared in the outmost block. Because external variables are globally accessible, they can be used instead of argument lists to communicate data between functions. Furthermore, because external variables remain in existence permanently rather than appearing and disappearing as functions are called and exited, they retain their values even after the functions that set them have returned. An external variable must be defined exactly once outside the function. Outside of any function, this sets aside storage for it. The variable must also be declared in each function that wants to access it. This states the type of the variable. I don't think C works that way anymore. The declaration may be an explicit extern statement, or it may be implicit from context. To make the discussion concrete, let us write the longest line program with line, longest, and max as external variables. This requires changing the calls, declarations, and bodies of these three functions. So I've always called these just global variables, but I guess in this book they call them external. So we got int max, and then we got our buffers and our prototypes. And then our main, we use extern int max to say, hey, I'm using the extern, but I don't think you have to do that. Pretty sure you can just reference it without even declaring it locally. The external variables in main, getLine, and copy are defined by the first lines of the example above, which states their type and storage and cause storage to be allocated for them. Syntactically, external definitions are just like definitions of local variables, but since they occur outside the functions, the variables are external. Before a function can use an external variable, the name of the variable must be made known to the function. One way to do this is to write an external declaration in the function. The declaration is the same as before except for the added keyword extern. I don't think that's true. Test extern.c main. We'll say var, not var, int num. How did they declare these? We'll just say int num, and then here we'll say num is equal to 5, and then we'll call print num. And then we'll have a void print num, and it's going to do println printf, and we'll just say num %d new line num. So this is demonstrating reading from inside this function and writing from another function. If we go make test, or sorry, build test extern, yeah, it works. You don't need to say extern. The K&R text uses the extern keyword inside of a function to declare that the function will use a global variable. However, I was under the impression that you could just reference the global variable without this declaration. Not if you pound include it. I'm guessing it's like a linker thing. If the global is defined in another file, but I pound include that file, then I won't need to use extern, right? It is only if I am compiling the other file as a separate .o to then link against later. Is that correct? So it's only if it's not declared anywhere, which most people just pound include the header files, so you won't see that. I guess that's good to know. All right, let's continue reading, because we only got a few pages left here. Specifically, one page left. The external variables main, get, line, and copy are defined. What was he talking about? In certain circumstances, the external declaration can be omitted. There we go. If the definition of an external variable occurs in the source file before its use in a particular function, then there is no need for an external declaration in the function. The external declaration in main, get, line, and copy are thus redundant. In fact, common practice is to place definitions of all external variables at the beginning of the source file and then omit any external declarations. If the program is in several source files and the variable is defined in file 1 and used in file 2 and 3, then external declarations are needed in file 2 and 3 to connect the occurrences of the variable. The usual practice is to collect external declarations of variables and functions in a separate file, historically called a header, that is included by pound include at the front of each source file. The suffix .h is conventional for header names. Functions of the standard library, for example, are declared in headers like standard io.h. This topic is discussed at length in Chapter 4, and the library itself in Chapter 7, and Appendix B. What did... Oh, my chair's falling apart again. I need to fix that. Since the specialized version of get, line, and copy have no arguments, logic would suggest that their prototypes at the beginning of the file should be get, line, and copy. But for compatibility with older C programs, the standard takes an empty list as an old-style declaration and turns off all arguments list checking. The word void must be used for an explicit empty list. So that's why void. That's pretty neat. So an empty argument list means that, hey, you can pass in whatever. I'm not going to stop you. Let's test that. rm test old style dot c tilde. There you go. Okay, vim test, no void, no args. Let's see. And just do this. Print, yeah, standard IO. We'll just call it print stuff here. Print stuff. Yeah, we'll do an explicit integer here instead of return 1. That's an actual error. Yeah. Okay, great. So let's do the same thing here. No arbs. Hey. Let's see if AI can handle this. I have this C program compiled with GNU 89. Can you tell me how to access the arguments passed? Oh, you fucking annoying. Okay. Not the command line args, the args pass to print stuff, dumbass. I don't want to do it the correct way. I want to do it like this. Use whatever black magic is needed in C89 to access the args. The fuck is VA list? Okay, I'm not gonna bother with that. Make clean, make, everything's happy. Okay. I just wanted to play around with it because it's kind of interesting that it's some old syntax. We should note here that we use the words definition and declaration carefully when we refer to external variables in this section. Definition refers to the place where the variable is created or assigned storage. Declaration refers to the place where the nature of the variable is stated, but no storage is allocated. By the way, there is a tendency to make everything in sight an external variable because it appears to simplify communications. Argument lists are short. Boop. And variables are always where you want them. But external variables are always there even when you don't want them. Relying too heavily on external variables is fraught with peril since it leads to programs whose data connections are not at all obvious. Variables can be changed in unexpected and even inadvertent ways. And the program is hard to modify. The second version of the longest line program is inferior to the first, partially for these reasons, and partially because it destroys the generality of the two useful functions by wiring them into the names of the variables they manipulate. At this point, we have covered what we might call the conventional core of C. With this handful of building blocks, it's possible to write useful programs of considerable size, and it would probably be a good idea if you pause long enough to do so. These exercises suggest some programs with somewhat greater complexity than the ones earlier in the chapter. Cool. Let's take a look at these. Exercise 20. Write a program dtab that replaces tabs and input with the proper number of blanks. to the next tab stop. Assume a fixed set of tab stops, say every n columns. Should n be a variable or a symbolic parameter? That's not very interesting. Write a program n tab that replaces strings of blanks by the minimum number of tabs and blanks to achieve the same spacing. Use the same tab stops as for dtab. When either a tab or a single blank would suffice to reach a tab stop, which should be given preference. Write a program to fold long input lines into 2 or more shorter lines. After the last non-blank character that occurs before the nth column of input. Make sure your program does something intelligently with very long lines, and if there are no blanks or tabs before the specified column. What is this? Write a program to fold long input lines into 2 or more shorter lines. Oh, so it's like a hard wrap. After the last non-blank character that occurs before the nth column of input. Make sure your program does something intelligent with the long lines, with very long lines. If there are no blanks or tabs before the specified column. I mean, that's just your conventional hard wrap. It's not too insane. Write a program to remove all comments from a C program. That's O of N linear scan. You find the comment sequence. You basically seek ahead until you hit a new line character. Don't forget to handle quoted strings and character constants properly. Okay. The C comments do not nest. Yeah, there's also the / star style comments that you would have to handle. Write a program to check a C program for rudimentary syntax errors like unbalanced parentheses, brackets and braces. Don't forget about quotes, both single and double, escape sequences and comments. This program is hard if you do it in full generality. Yeah, it's static analysis program. You'd either have like a state machine or some type of stack-based approach. Function calls are a decent stack. You can leverage the function call stack. There's a lot you could do. I'm going to highlight a couple of these that seemed interesting to me, like I said I would do. So 23 and 24 sound interesting to me just because they're programs that manipulate source code. And I would like to do a little bit more work on that. All right, chapter 2, types, operators, and expressions. I'll take a quick bio break, and then I'll be back to start on that. I get to know about the time by the window outside view, yeah. Sometimes it's overcast. But yeah. It is a little bit overcast today. All right, I'm going to take a quick break, but I'll be back. Uno momento. All right. Let's start on chapter 2. In fact, before we do that, I'm going to make a commit because we finished chapter 1. And we got a lot done here. Look at all these test files. Oops. All these test files here. We compared a bunch of integer sizes. What was this count? Get diff cache. This thing here. Oh, this is just a little script that compiled and did a delta of those two. That was nice. The count thing. Oh, I just did that that was a program in the book. I just did that to test that syntax for for loop. Single line for loop with no body. The histogram stuff, that was like really fun writing. I did a vertical and horizontal histogram. Got to use enums. We tested out how EOF was defined. Tested out externs, different int sizes, not having arguments in your function definition, but still allowing it to be called. And then the old style funcs, C89. I think my favorite thing that I did so far was this histogram. Build histogram, this thing. That was fun. And then you give it a bunch of test data, blah, 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 blah. And then hit Control D, and it prints out a histogram of the frequency of the characters and word blanks. And it does it vertically instead of horizontally. Horizontally is easy to implement. Vertical is not. And it's scaled appropriately. Cool. Let's go ahead and make a commit. Git CI, say finish chapter 1. Do 01. Keep it consistent. Yep, looks good to me. mkdir chapter 2. Okay. Types, operators, and expressions. Variables and constants are the basic data objects manipulated in a program. Declaration lists the variables to be used and state what type they have and perhaps what their initial values are. Operators specify what is to be done to them. Expressions combine variables and constants to produce new values. The type of an object determines the set of values it can have and what operations can be performed on it. These building blocks are the topics of this chapter. The ANSI standard has made many small changes and additions to basic types and expressions. There are now signed and unsigned forms of all integer types. Let me read that. The ANSI standard has made many small changes and additions to basic types and expressions. There are now signed and unsigned forms of all integer types, and notations for unsigned constants and hexadecimal character constants. Floating point operations may be done in single precision. There is also a long double type for extended precision. String constants may be concatenated at compile time. Oh, interesting. I didn't know that. Enumerations have become part of the language. Formalizing a feature of long-standing. Objects may be declared const, which prevents them from being changed. The rules for automatic coercions among arithmetic types have been augmented to handle a richer set of types. Lots of new stuff. It's funny reading this book. You get the feeling of like this language is still in flux, still being developed. And now it's just kind of like a permanent fixture that hasn't really changed much in decades. Variable names. Although we didn't say so in Chapter 1, there are some restrictions on the names of variables and symbolic constants. Names are made up of letters and digits. The first character must be a letter. The underscore counts as a letter. It is sometimes useful for improving the readability of long variable names. Don't begin variable names with underscores, however, since library routines often use such names. Uppercase and lowercase letters are distinct. So X and X are two different names. Traditional C practice is to use lowercase for variable names and all uppercase for symbolic constants. At least the first 31 characters of an internal name are significant. For function names, and what does this line mean? At least the first 31 characters of an internal name are significant. For function names and external variables, the number may be less than 31. Because external names may be used by assemblers and loaders over which the language has no control. Interesting. For external names, the standard guarantees uniqueness only for 6 characters and a single case. Keywords like if, else, and float, etc. are reserved. You can't use them as variable names. They must be in lowercase. It's wise to choose variable names that are related to the purpose of the variable and are unlikely to get mixed up typographically. We tend to use short names for local variables, especially loop indices, and longer names for external variables. So I'm going to go back to this page. One thing I'm going to write in the margin here is just like I wonder if this limit is why so many C programs use short variables names. I want to get better at writing in my books. That's why I buy paper books, so I can write in them. Okay. Data types and sizes. There are only a few basic data types in C. Char, which is a single byte capable of holding one character in the local character set, which is often UTF-8. And it wouldn't be a character if it's UTF-8. It would be bytes. So char is basically a single byte. Int, an integer typically reflecting the natural size of integers on the host machine. Float, single precision floating point. Double precision floating point. In addition, there are a number of qualifiers that can be applied to these basic types. Short and long apply to integers. Short int, sh, long int, counter. The word int can be omitted in such declarations and typically is. The intent is that a short and long should provide different lengths of integers where practical. Int will normally be the natural size for a particular machine. Short is often 16 bits, long is 32 bits, and int either 16 or 32. Each compiler is free to choose appropriate sizes for its own hardware, subject to the restriction that shorts and ints are at least 16 bits. Longs are at least 32 bits, and short is no longer than int. which is no longer than long. The qualifier signed or unsigned may be appended to char, or any integer. Unsigned numbers are always positive or 0. They obey the laws of arithmetic, modulo 2 to the power n, where n is the number of bits in the type. So for instance, if chars are 8 bits, unsigned char variables have values between 0 and 255. Well, signed chars have values between negative 128 and positive 127 in 2's complement machine. Whether plain chars are signed or unsigned is machine dependent. But printable characters are always positive. The type long double specifies extended precision floating point. As with integers, the size of floating point objects are implementation defined. I'm going to be back after some time to catch up on the stream on YouTube. Oh, okay, cool. The standard headers limits.h and float.h contain symbolic constants for all of these sizes. You should watch it on 2x speed. 2x or 3x speed. Okay. Let's talk about floats and headers. Standard headers limits.h and float.h contain symbolic constants for all of these sizes, along with other properties of the machine and compiler. These are discussed in Appendix B. Exercise 2.1. Write a program to determine the ranges of char, short, int, and long variables, both signed and unsigned, by printing appropriate values from standard headers and by direct computation. Harder if you compute them. Determine the ranges of various floating point types. Okay. Well, I could do that. I did a program that was similar already, but it just gives you the amount of bits instead of the ranges. So the ranges wouldn't be too difficult for most of the integer types. The floating point ranges, I would have to look up the bit patterns for the different floating point sizes and then set all those bits appropriately. But I'll go ahead and highlight that one. That one's not too hard, but it's not super interesting to me right now. Constants. An integer constant like 124 is an int. The long constant is written with a terminal L. Looks like a 1. Terminal L or L as 124 or 1, 2, 3, 4, 5, 6, 7, 8, 9 L. An integer too big to fit into an int will also be taken as a long. Unsigned constants are written with a terminal U or U as a suffix. U1 or UL indicates an unsigned long. Oh, sorry, UL lowercase or UL uppercase indicates an unsigned long. That's very similar to other languages. You can see where C has influenced almost every modern language in its constant declarations here. Floating point constants contain a decimal point, 123.4, or an exponent 1e minus 2, or both. Their type is double unless suffixed. The suffix f or f, lowercase f or uppercase f, indicate a float constant. Lowercase l or uppercase L indicate a long double. The value of an integer can be specified in octal or hexadecimal instead of decimal. A leading 0 on an integer constant means octal. A leading 0x or 0 capital X means hexadecimal. For example, decimal 31 can be written as octal 037 in octal, and 0x 1f or 0 capital X 1 capital F in hex. Octal and hexadecimal constants may also be followed by a capital L to make them long, and capital U to make them unsigned. So you can have a 0xFUL. Oh, interesting. So 0xFUL is an unsigned long constant with the value 15 decimal. A character constant is an integer written as one character within single quotes, such as x. The value of a character constant is the numeric value. Sorry, I lost my track. The value of the character constant is the numeric value of the character in the machine's character set, which is UTF-8 nowadays for almost everything. For example, in the ASCII character set, the character constant 0 has the value 48, which is unrelated to the numeric value 0. If we write quote 0 instead of a numeric value like 48, that character depends on character set. The program is independent of the particular value and easier to read. Character constants can participate in numeric operations just as any other integers, although they are most often used in comparisons with other characters. Certain characters can be represented in character and string constants by escape sequences like /n for new line. Sorry, \n for new line. These sequences look at like two characters but represent only one. In addition, an arbitrary byte-sized bit pattern can be specified by /000, where 000 is 1 to 3 octal digits, or by \xhh, where hh is 1 or more hexadecimal digits. So we might define VTAB as octal 13 or octal 07, or in hexadecimal as \xb or \x7. So these characters here after the X are known as nibbles because they're half a byte. They're 4 bits. Thus nibble. A complete set of escape sequences is the alert bell, backspace, form feed, new line, carriage return, horizontal tab, vertical tab, / itself, question mark. Don't know why that needs to be backslashed. Single quote, I guess it's for escaping purposes if you want to make sure it doesn't get confused. And then there's arbitrary octal and hexadecimal numbers. The character constant \0 represents the character with the value 0. The null character. \0 is often written instead of 0 to emphasize the character nature of some expressions, but the numeric value is just 0. A constant expression is an expression that involves only constants. Such expression may be evaluated during compilation rather than runtime, and accordingly may be used in any place that a constant can occur, as in pound define max line 1000, character line max line +1, or pound define leap 1, int days. Actually, let's look at this. Okay, that makes sense. How many days in the year, whether it's leap year or not. I mean, I don't think you would ever do that at compile time for most things. You would just determine at runtime if it's a leap year or not. A string constant or string literal is a sequence of 0 or more characters surrounded by double quotes, as in I am a string or empty string. The quotes are not part of the string but serve only to delimit it. The same escape sequences used in character constants apply in strings. \quote represents the double quote character. String constants can be concatenated at compile time, just without any operator in between them. Is useful for splitting long lines across several source lines. Technically, a string constant is an array of characters. The internal representation of a string has a null character at the end, so the physical storage required is one more than the number of characters written between the quotes. This representation means that there is no limit to how long a string can be, but programs must scan a string completely to determine its length. The standard library function strlen returns the length of its character. This is why Pascal strings are better than C strings, because Pascal string stores the length as part of the header of the string, and you don't have to compute it by scanning the string linearly. Turns it to an O of 1 operation instead of O of n. String arguments S, excluding the terminal \0. Here is our version. So we take in a character array, return an integer. We declare I as the integer we're going to return. We set it to 0. And then we go through the loop while the character at the index I is not equal to the null character. We advance I. As soon as it is equal to the null character, then we return the I, which will give us the length of the string, not including the null byte, which is what we want. Strlen and other string functions are declared in the standard header string.h. Be careful to distinguish between a character constant and a string that contains a single character. The character constant of x is not the same as the string constant x. The former is an integer used to produce the numeric value of the letter x in the machine's character set. The latter is an array of characters that contains one character, the letter x, and a null byte at the end. There is one other kind of constant, a enumeration constant. Enumeration is a list of constant integer values, as in enum bool no yes. First name in the enum has a value 0, next 1, and so on, unless explicit values are specified. If not all values are specified, unspecified values continue the progression from the last specified value, as in the second of these examples. So we got enum escapes and enum months. But months we start from 1 and count upwards. And then escapes, we just assign them manually. Names in different enumerations must be distinct. Values need not be distinct in the same enumeration, obviously. Like I said, it isn't too obvious. Enumerations provide a convenient way to associate constant values with names, an alternative to pound define, with the advantage that the values can be generated for you. Although variables of enum types may be declared, compilers need not check that what you store in such a variable is a valid value for the enumeration. Nevertheless, enumeration variables offer the chance of checking and so are often better than pound defines. Let me reread that. Enumerations provide a convenient way to associate constant values with names, an alternative to pound define, with the advantage that the values can be generated for you. Although variables of enum types may be declared, compilers need not check that you store in such a variable is a valid value for the enumeration. Nevertheless, enumeration variables offer the chance of checking and so are often better than defines. So most compilers are going to do the checking nowadays. In addition, a debugger may be able to print values of an enumeration variable in their symbolic form versus just the numeric form. That's cool. All right. Declarations. Let's see how many pages we've got left here. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 14 and a half. So I can get through that before the end of the day here. So we have at least 2 chapters done. Okay. Declarations. All variables must be declared before use, although certain declarations can be made implicitly by context. A declaration specifies a type and contains a list of one or more variables of that type, as in int lower upper step, char C line array of 1000 elements. Variables can be distributed among declarations in any fashion. The list above could equally be written as so-and-so. Makes sense? This latter form takes more space, but is convenient for adding a comment to each declaration or for subsequent modification. A variable may also be initialized in its declaration. If the name is followed by an equal sign and an expression, the expression serves as an initializer, as in these examples here, all constants on the right-hand side. If the variable in question is not automatic, the initialization is done once only, conceptually before the program starts executing, and the initializer must be a constant expression. An explicitly initialized automatic variable is initialized each time the function or block it is in is entered. The initializer may be any expression. External and static variables are initialized to 0 by default. Automatic variables for which there is no explicit initializer have undefined garbage values. The qualifier const can be applied to the declaration of any variable to specify that its value will not be changed. For an array, the const qualifier says that the elements will not be altered. So you can say const double E or const char message warning. The const declaration can also be used with array arguments to indicate that the function does not change that array. The result is implementation defined if an attempt is made to change a const. I think most compilers can detect that now and give you a compile time warning. Arithmetic operators. The binary arithmetic operators are plus, minus, star, and slash, and the modulus operator, %. Integer division truncates any fractional part. The expression so-and-so produces the remainder when x is divided by y, and thus is 0 when y divides x exactly. For example, a year is a leap year if it is divisible by 4, but not by 100, except for that years that are divisible by 400 are leap years. Therefore, this complex expression with modulo and Boolean comparisons, the % operator cannot be applied to float or double. The direction of truncation for integer division is the sign of the result for modulo. And the sign of the result for modulo are machine dependent for negative operands, as is the action taken on overflow and underflow. The binary plus and minus operators have the same precedence, which is lower than the precedence of star, division, and modulo, which is in turn lower than the unary plus and minus. Arithmetic operators associate left to right. Table 2.1 at the end of this chapter summarizes precedence and associativity for all operators. Relational and logical operators. The relational operators are greater than equals, less than equals. They all have the same precedence. Just below them in precedence are the equality operators, double equal and not equal. Relational operators have lower precedence than arithmetic operators. So an expression like I is less than limit minus 1 is taken as I is less than limit minus 1, where limit minus 1 is evaluated first and then compared to I, as would be expected. More interesting are the logical operators and or. Expressions connected by and or are evaluated left to right. The evaluation stops as soon as the truth or falsehood of the result is known. Most C programs rely on these properties. For example, there's a loop in the form of the input function. This is short circuiting. For example, here is a loop in the input function getLine that we wrote in chapter 1. Before reading the new character, it is necessary to check that there is room to store it in an array S. So the test I is less than limit minus 1 must be made first. Moreover, if the test fails, we must not go on and read another character. Similarly, it would be unfortunate if C were tested against EOF before getCar is called. Therefore, the call and assignment must occur before the character in C is tested. The precedence of AND is higher than that of OR, and both are lower than relational and equality operators. So expressions like I is less than limit minus 1 and C is equal to getCar is not equal to new line and C is not equal to EOF. Okay, trying to think how this would happen. Yeah, those are 3 separate ones. Need no extra parentheses, but since the precedence of not equal is higher than assignment, parentheses are needed. Yeah. To achieve the desired result of assignment to C and then comparison with new line. By definition, the numeric value. Am I on the right? Oh, sorry, I did not advance the page here. My bad. So I am here. By definition, the numeric value of a relational or logical expression is 1 if the relation is true and 0 if the relation is false. The unary negator operator bang converts a non-zero operand into 0 and a 0 operand into 1. The common use of the construction is in constructions like if not valid rather than if valid is equal to 0. There's also the bang bang, which forces values into 0 or 1, which just applies the not twice. It's a double application of the unary operator. It's hard to generalize about which form is better. Constructs like not valid read nicely, if not valid, but more complicated ones can be hard to understand. Exercise 2.2, write a loop equivalent to the for loop above without using and or. I'm good. That doesn't sound interesting. Type conversions. So this is an area where I honestly, there's a couple pages dedicated to this. I honestly don't know a lot of the type conversion rules off the top of my head for any language that I use, to be honest. That's why I like languages like Go, where it has to be explicit instead of having implicit type conversion. Everything is explicit. But yeah, let's see what the rules are in C here. When an operator has operands of different types, they are converted to a common type according to a small number of rules. In general, the only automatic conversions are those that are convert a narrower operand into a wider one without losing information, such as converting an integer to floating point, an expression like f plus I. Expressions that don't make sense, like using a float as a subscript, are disallowed. Expressions that might lose information, like assigning a longer integer type to a shorter or a floating point type to an integer, may draw a warning, but they are not illegal. It's interesting. A char is just a small integer, so chars may be freely used in arithmetic expressions. This permits considerable flexibility in certain kinds of character transformations. One is exemplified by this naive implementation of the function a to I, which converts ASCII to integer. That's the way I interpret that, which converts a string of digits to its numeric equivalent. Boop, 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 boop. A to I converts S to an integer, ASCII to integer. So we declare I, which is our indice, into our loop, and we declare N, which is our return value, both as integers. we initialize n to be 0, and then basically for each character, left to right, we do the condition where we grab the integer and say, hey, are you greater than or equal to 0? And also less than or equal to 9, then that means that you're numeric. In which case, we take that value, subtract off the character 0, which will basically convert that to a numeric value, and then add that to n times 10. And n times 10 basically will add a 0 to the right hand side of the digit. So we're basically multiplying n times 10 to give it a 0, and then we're adding in the single digit place. And we're doing that multiple times, just pushing the digits along. As we discussed in chapter 1, the expression s sub I minus the character 0 gives the numeric value of the character stored in s sub I, because the values of 0, 1, etc. form a contiguous increasing sequence. Another example of char to int conversion is the function lower, which maps a single character to lowercase for the ASCII character set. The character is not if the character is not an uppercase letter, lower returns it unchanged. So lower takes in the character. It says, hey, are you greater than or equal to the uppercase character A, and also less than or equal to the uppercase character Z? That means that you're an uppercase character, in which case I'll take the character and I'll add the delta between the lowercase character A and the uppercase character A, which will effectively convert it to a lowercase character. Otherwise, we just return it. This works for ASCII because corresponding uppercase and lowercase letters are at a fixed distance apart as numeric values. So the other thing that you could do, I remember there's like a binary operation you can do on characters. I think let's see if I can remember this off the top of my head. So if you say you have the character A, I think you can XOR it with, is that how you XOR? Oh, but you have to use the ordinal values. Ord of A, and then you ord of A, and then you have to convert this to a char. Why can't you use a char? Oh, sorry, CHR, not CHAR. This is Python. So I think you XOR it, if I remember correctly. No, you XOR it with space. That's right. So you can define a toggle case. It takes in C character and returns the char of the ordinal of the character you gave it, XORed with the ordinal of the character space. And yeah, now you can just call it toggle case on, say I have like a W, capital W. Now convert it to lowercase w. If I have a lowercase w, it converts it to uppercase. If I have like a R, a lowercase q, and that's because we're using XOR. I think if we subtract space, I think that's, or and if we and it, oops, I did a double and instead of a single and. I think if we just use a single ampersand. Wait a minute, that's not what I wanted. What is the binary pattern for the character space? Okay, so we would use an OR to set it. So if I had an uppercase A here, or lowercase a, doesn't matter. Wait a minute. What is the A? If I do bin of ord of A, and bin of ord of A, and bin of ord of space. So the difference between these two is that one bit there. So I would think OR between the lowercase would convert it to an uppercase, or sorry, between the uppercase. Oh, it does. For some reason, my brain didn't register it. So this is effectively the same as all this math here. It takes an uppercase character, so we can define to lower C, and then just return this expression here. If I can select it. Can I not? Okay, I can't do that. Let's do return char of ord of C, ord with ord of space. And then I can say to lower of any character here. A, oops, I need to actually terminate my string. Or Z, or Q. But if it's already there, it doesn't toggle it. So that's the difference. So OR would be converting from upper to lower. XOR toggles. I wonder if we could do a to upper. So let's bring back that expression, which is here. So you want to go to upper. I would think it would be and, but it actually converts it to space itself. So ord of A, I have to convert this to binary. Binary. Ord of A and ord of space. So what we want to do to go from lower to upper is to flip this one bit here. Which is set in the space character. So we can't use and because all these zeros are just going to zero everything out. And then we'll just get the one here. So you get two values, space and zero, which is definitely not what we want. So and is right out. What we want is to set the bit so OR would work to set the bit, right? To go to lower, but what we want to do is so we want to OR of the negation maybe. Let's try that. OR of the negation. I think tilde is the negation operator. What is the negation operator for Python? Python bitwise negation. What is tilde? Go away, please. Yeah, I thought there was tilde. But for some reason it didn't like... Oh, because it's already like that. Okay. In Python, if I have an integer with a single bit set, and I want to use that as a mask on another integer to make sure that single bit is not set to 0. What would the binary operation be? I think it's a negation and an or. It says a negation and. That would make sense. I just can't negate it though. It says char arg. Well, we'll take away the char. What is this ord of space? What does that convert to? If we say bin of ord space, it's negating the value, it looks like. Yeah. Because it has a stupid negative sign in front of it. I don't like that. So if we do this expression and I give it an and here, 65, and I convert that to char. Hey, it worked. Okay, so it does work. But not when I put the or here, because that's like not a valid value. Okay. All right, that makes sense. If I had a piece of paper, I could have written it out faster than it took me to do it in the Python interpreter. But yeah, just using the character space, because space has a single bit set, and manipulating that space, you can then use binary operators, or bitwise operators, I should say, to manipulate that character to either toggle its case, make it lower, or make it upper. All right. Let's get out of here. Let's go ahead and like copy this then, because I'm kind of interested in like saving this stuff. To lower, and then there's a toggle case. Yeah. Vim case.py. So we'll just go delete all that. Let's go down to lower, and then to upper, which will take it with ampersand, or no, yeah, ampersand and negation. And we're going to just assert that toggle underscore case of, we'll do it like W is equal to W. W is equal to W. And then we'll do another one here, to upper of W. And then we'll do kind of like keeping these parameters the same here. To lower. Yeah. And I'll just do a hash bang user bin env python. And we'll say chmod plus x case. Plus x case pi, and then if I say change one of these, like say I change this to capital W, you could see like the assertions would fail. So that's how you handle case stuff with bitwise operators and the space character. And the expression is a little bit nicer in C, because you don't have to do this explicit conversion between like the character, which is actual string in Python, and the ordinal, and then back to the character. All right. Let's pick up where we left off. This works for ASCII because corresponding uppercase and lowercase characters are a fixed distance apart as numeric values, and each alphabet is contiguous. There is nothing but letters between A and Z. This latter observation is not true of the EBCDIC character set. However, so this code would convert more than just letters in EBCDIC. The standard header ctype.h described in Appendix B defines a family of functions that provide tests and conversions that are independent of character set. For example, the function toLower returns the lowercase value of C if C is uppercase. So toLower is a portable replacement for the function lower shown above. I don't care about portability. Similarly, the test C is greater than or equal to the 0 byte, or the 0 character, I should say, and C is less than or equal to the 9 character, it can be replaced by isDigit C. We'll use ctype.h functions from now on. There is one subtle point about the conversion of characters to integers. The language does not specify whether variables of type char are signed or unsigned quantities. When a char is converted to an int, can it ever produce a negative integer? The answer varies from machine to machine, reflecting differences in architecture. On some machines, a char where leftmost bit is 1 will be converted to a negative integer, a signed extension. On others, a char is promoted to an integer by adding zeros to the left end, and thus is always positive. Definition of C guarantees that any character in the machine's standard printing character set will never be negative. So these characters will always be positive quantities and expressions, but arbitrary bit patterns stored in character variables may appear to be negative on some machines, yet positive on others. For portability, specify signed or unsigned if non-character data is to be stored in character variables. Relational expressions like I is greater than J and logical expressions connected by ampersands and ors are defined to have the value 1 if true and 0 if false. Thus, the assignment D is equal to C greater than or equal to 0 and C is less than or equal to 9 sets D to 1 if C is a digit and 0 if not. However, functions like isDigit may return any non-zero value for true. In the test part of if, while, for, etc., true means non-zero. This makes no difference. Implicit arithmetic conversions work much as expected. In general, if an operator like plus or star that takes 2 operands, a binary operator, as operands of different types, the lower type is promoted to the higher type before the operation proceeds. The result is of the higher type. Section 6 of the Appendix A states the conversion rules precisely. If there are no unsigned operands, however, the following informal set of rules will suffice. If either operand is long double, convert the other to long double. Otherwise, if either operand is double, convert the other to double. Otherwise, if either operand is float, convert it to float, convert it to char, and short to int. Otherwise, convert char and short to int. Then, if either operand is long, convert the other to long. Notice that floats in an expression are not automatically converted to double. This is a change from the original definition. In general, mathematical functions like those in math.h will use double precision. The main reason to use float is to save storage in large arrays, or less often, to save time on machines where double precision arithmetic is particularly expensive. Conversion rules are more complicated when unsigned operands are involved. The problem is that comparisons between signed and unsigned values are machine dependent because they depend on the sizes of the various integer types. For example, suppose that int is 16 bits and long is 32 bits. Then -1 long is less than 1u, because 1u, which is an int, is promoted to a signed long, but -1l is greater than a signed long because -1l is promoted to an unsigned long and thus appears to be a large positive number. Okay. Conversions take place across assignments. The value to the right side is converted to the type on the left, which is the type of the result. A character is converted. Basically, be explicit with your conversions. That's what I'm taking away from this. A character is converted to an integer, either by sign extension or not, as described above. Long integers are converted to shorter ones, or to characters by dropping the excess high order bits. Thus, in int I char C, C assigned to I, C gets up converted, and I to C, I gets down converted. But the value of C is unchanged. This is true. Yeah, because it got up converted on the first assignment and then it got down converted on the second assignment. So it's unchanged at the end. This is true whether or not sign extension is involved. Reversing the order of the assignment might lose information, however. Exactly, because you're going to go down first before you go up. If x is float and I is int, then x is equal to I and I is equal to x. Both cause conversions. Float to int causes truncation of any fractional part. When double is converted to float, whether the value is rounded or truncated is implementation dependent. Since an argument of a function call is an expression, type conversions also take place when arguments are passed to functions. In the absence of a function prototype, char and short become int, and float becomes double. This is why we have declared function arguments to be int and double even when the function is called with char and float. Finally, explicit type conversions can be coerced in any expression with a unary operator called a cast in the construction type name expression. So like in Go, you have to explicitly do all your conversions. You don't get any implicit conversions. I think there's things like polymorphism, where you can receive like an integer, or even like with generics, you can do generics now in Go. But like if you accept like an integer and you pass in a floating point number, you have to explicitly convert it to an integer at the site of the call. Whereas in C is just like, I'll convert it for you, which is not great. Finding explicit type conversions can be coerced to an expression with a unary operator called a cast. In the construction type name expression, the expression is converted to the name type by the conversion rules above. The precise meaning of the cast is as if the expression were assigned to a variable of the specified type, which is then used in place of whole construction. For example, the library tune square root expects a double argument and will produce nonsense if inadvertently handled something else. Square root is declared in math.h. If n is an integer, we could use the square root double n to convert the value of n to a double before passing it to square root. Note that the cast produces a value of n in the proper type. N itself is not altered. The cast operator has the same high precedence as other unary operators, as summarized in the table at the end of this chapter. If arguments are declared by a function prototype, as they normally should be, the declaration causes automatic, Wait a minute, am I on the right page here? Sorry, I didn't keep on doing that. Apologize. So basically, like this page introduces the cast. Oh, I got a spammer here. I need a block. I get so many freaking spammers. So this page is just talking about how the integer is basically integer is bigger than character. So when you take the character and you assign it into an integer, it's getting upcast. It's getting up converted into an integer. And then when you take that integer and assign it back to the character, it's getting down converted to a character. And so there's no loss in information here. Like as C becomes an integer and then goes back to being a character, there's no loss of information there. But if you inverted these two and you took I and assigned it to character, that's a down conversion. So you're going to lose information potentially. So just something to be aware of with the conversions. Then these type name expression is like the canonical casting syntax. It's pretty much in every language, any language that derives from C. So it's how you like cast or coerce different expressions into different types. And they give an example here of square root double n, because square root takes an integer, or sorry, square root takes a double and n is an integer. If you gave it n, the compiler would blow up, say, hey, I don't know how to convert this thing. And so you explicitly cast it. If arguments are declared by the function prototype, as they normally should be, the declaration causes automatic conversion of any arguments when the function is called, thus giving function prototype for square root double square root double. The call root 2 square root 2 coerces the integer 2 into double value 2.0 without the need for a cast. Okay. So it does know how to convert an integer to a double. I thought this was taking a constant, which is typeless, and converting it to a double, which Go will do as well, but not for a non-constant value. All right. The standard library includes a portable implementation of a pseudo-random number generator and a function for initializing the seed. The former illustrates a cast. So unsigned long int next. Is equal to 1. And then we have rand void returns an int. So next times this huge number plus some offset. What? This is a pseudo-random number. I wonder how this thing works. It probably uses like integer overflow or something. So you take next, you divide it by, what was this, 2 to the power of 16? And then you modulo math it. So I guess that's the random part, the pseudo-random part, is the modular math. Huh. I don't think it's cryptographically secure. Random number. Write the function h2i, which would be hexadecimal digits to integer, including an option for ox and ox into its equivalent integer value. The allowable digits are 0 through 9, a through f, and a through f. I'm good. I'm not going to do that one. Increment and decrement operators. C provides two unusual operators for incrementing and decrementing variables. The increment operator plus plus adds 1 to its operand, while the decrement operator minus minus subtracts 1. We have frequently used plus plus to increment variables, such as in if C is equal to new line character, then we plus plus N1 or NL. The unusual aspect is that plus plus and minus minus may be used either as prefix operators before the variable or postfix after the variable. In both cases, the effect is to increment n, but the expression plus plus increments n before the value is used, while n plus plus increments n after the value has been used. This means that in the context where a value is being used, not just the effect, plus plus n and n plus plus are different. If n is 5, then x is equal to n plus plus would make x equal to 4, or x equal to 5. But x is equal to plus plus n would make it equal to 6. In both cases, n becomes 6. The increment and decrement operators can only be applied to variables and expression like I plus j plus plus is illegal. Okay. In a context where no value is wanted, just the incrementing effect, as in C is equal to so-and-so plus plus, prefix and postfix are the same, but there are situations where one or the other is specifically called for. For instance, consider the function squeeze SC, which removes all occurrences of the character C from the string S. So we pass in our string as a character array, and we give it the character C, and we go over all the characters, setting ij is equal to 0 initially, and then we test to see if it's a null byte. If it is, we abort, and we set j equal to the null byte. So j is like where we would otherwise be in the string if we didn't remove these other bytes. I think that's what it's saying. If s sub I is not equal to c, then we just advanced. We say s sub I, we copy that into j plus. So let's do an example where they're both 0. So they're both 0, we have a string. We go in, it's not equal to c. So then we take our current value and we write it to the next value? That doesn't make sense. Oh, okay. It's because it's a post increment. This is exactly what they're saying. It's a post increment, so it'd be assigning it to the current value. And then if it's not, then we don't increment j at all. And we continue on. And at the end, we put the null byte at j. That makes sense. That's a really elegant way of doing it. I would have done it less elegantly. Each time a non-C occurs, it is copied into the current j position, and only then is j incremented to be ready for the next character. This is exactly equivalent to saying copy and then j plus plus. I would have done it that way. Another example of a similar construction comes from the getLine function that we wrote in chapter 1, where we can replace if characters equal a new line, assign it into the array, and then increment by a more compact. Yeah, I mean, I kind of feel like this is code golf a little bit. Like, why not just do it the longer way, and it's easier to understand. You don't have to think through, like, is this incrementing and then returning it, or returning it and then incrementing it. Like, I can see why people get annoyed by this stuff. As a third example, consider the standard function stircat st, which concatenates the string t to the end of the string s. Stircat assumes that there is enough space in s to hold the combination. As we have written it, stircat returns no value. The standard library returns a pointer to the resulting string. Okay. Concatenate t to the end of s. S must be big enough. Void stircat, char star, okay. All right, let's try to figure this out on our own without the book's help. So we got these two characters. They come in as char arrays. And we're trying to take s and add it to the end of t. We initialize two indices to 0. Basically, the first part of the algorithm is just to seek to the point where we have a null byte in the first string. So find the end of s. And then we start copying. And we do that by taking I and j. So j is pointing to the 0th character in the t, and I is pointing to wherever the null byte is. So we do the copy and then we increment, which makes sense, until we hit the null byte at the end. As each character is copied from t to s, the postfix operator is applied to both I and j to make sure that they are in the position for the next pass through the loop. Exercise 2.4. Write an alternative version of squeeze that deletes each character in S1 and matches any character in, I don't want to do that. Write a function any S1, S2, which returns the first location in the string S1 where any character from the string S2 occurs. Or -1 if S1 contains no character from S2. The standard library function stir pburk does the same job, but returns a pointer to the location. Alright, I'm not really interested in doing those string functions. So we got bitwise operators, assignment operators, and expressions, conditional expressions, precedence and order evaluations, along with the precedence table, and that's it. Alright, bitwise operators. C provides 6 operators for bit manipulation. These may only be applied to integral operands, that is char, short, int, and long, whether signed or unsigned. So I got bitwise and, bitwise inclusive or, bitwise exclusive or, left shift, right shift, and one's complement unary. One's complement, which is a negation, basically. The bitwise and operator and is often used to mask off some set of bits. For example, and that sets to 0 all but the low order 7 bits of n. The bitwise operator or is used to turn bits on. So we can OR things together to turn them on. Sets to 1 in X the bits that are set to 1 in set on. The bitwise exclusive OR operator sets to 1 in each bit position where its operand have different bits, and 0 where they have the same. Make sense? Okay, next page. I remember this time. All right. One must distinguish the bitwise operators and and or from the logical operators and or. which imply left to right evaluation of a truth value. For example, if x is 1 and y is 2, then x and y is 0, while x and y is 1. The shift operators left and right perform left and right shifts to their left operand by the number of bits positions given by the right operand, which must be positive. Thus, x left shifted by 2 shifts the value x left by 2 positions, filling vacated bits with 0. This is equivalent to multiplication by 4, assuming you don't overflow the amount of bits that you have. Right shifting signed quantity will fill with signed bits, arithmetic shift, on some machines, and with 0 bits, logical shift on others. The unary operator yields the ones complement of an integer. These are all... No. There's multiple unary operators. I don't know why he calls it the unary operator. But he says the unary operator yields the ones complement of an integer. That is, it converts each 1 bit to a 0 bit and vice versa. For example, sets the last 6 bits of x to 0. Note that x and negation of 7077 is independent of word length and is thus preferable to, for example, x and this other thing, which assumes that x is a 16-bit quantity. The portable form involves no extra cost since the negation of octal 77 is a constant expression that can be evaluated at compile time. As an illustration of some of the bit operators, consider the function getBits that returns the right adjusted end bit field of x that begins at position p. So getBits, we give it xpn. It returns the right adjusted n bit field of x that begins at position p. We assume that bit position 0 is at the right end and that n and p are sensible positive values. For example, getBits x43 returns 3 bits in bit position 4, 3, and 2 right adjusted. Honestly, I have no idea what this thing does. The expression x right shifted p plus 1 minus n moves the desired field of the right end to the word, right end of the word. Then the negation of 0 is all 1 bits, shifting it left n bit positions, places zeros in the rightmost n bits, complementing that with negation makes a mask with ones in the rightmost n bits. That makes sense. I get the right hand side here. This thing is basically giving you n bits on the right hand side, the least significant bits, and then you AND that with x bit shifted by p plus 1 minus n. I don't understand how this is useful. I like the n part. The p, x is the value. The n part is the amount of bits that you're going to get on the right hand side, like the amount of bits total that you're going to get. And then p looks like it's taking x and bit shifting it by p on the right hand side. So it's how many times you want to bit shift it. Let me reread this paragraph because I didn't really quite understand how this is useful. Oh, from position P. Okay. I can see how that'd be useful. Getting n bits from position P. Okay. That makes sense. All right, we got some exercises here. Let's see if there's anything that's interesting. Write a function set bits that returns x with a number n bits that begin in position. That's kind of interesting. I'm going to highlight that. Write a function invert that returns x with the n bits that begin at position P inverted, leaving the others unchanged. That's kind of cool. I like these little functions. Write a function right rotation that returns the value of the integer x rotated to the right by n bit positions. I'm going to do all three of these. I highlighted them. I'm just not going to do them now because I want to get the reading done for this chapter. And then when we get to the end, I'll put a little note here. 2.6 through 2.8. Okay. So we'll come back to these. All right, the next section is about assignment operators and expressions. Expressions such as I is equal to I plus 2, in which the variable on the left-hand side is repeated immediately on the right, can be written in the compressed format I is plus equal to 2. The operator plus equal is called the assignment operator, called an assignment operator. Most binary operators, operators like plus that have a left and right hand operand, have a corresponding assignment operator equals, where op equals, where op is one of the plus minus star divide mod bit shift. I didn't know that was a assignment one. That's some interesting stuff. If expression 1 and expression 2 are expressions, then expression op equals expression 2 is equivalent to expression 1 is equal to expression 1 op expression 2. Except that expression 1 is computed only once. Notice the parentheses around expression 2. I guess that's for precedence, maybe. Nah. All right. Yeah, it is for precedence. Because if you didn't have those parentheses, you might break precedence. As an example, the function bit count counts the number of 1 bits in its integer argument. So we're just going to bit shift over x by 1 and assign that to x. So if b is equal to 0, x is not equal to 0, we shift it over by 1. And if that x has a 1-bit set, then we increment it. Okay, that makes sense. Declaring the argument x to be unsigned ensures that when it is right shifted, vacated bits will be filled with zeros, not signed bits, regardless of the machine that program is run on. quite apart from consciousness. What is this? Consciousness. Assignment operators have the advantage that they correspond better to the way people think. We say add 2 to I, or increment I by 2, not take I, add 2, then put the result back in I. Thus, the expression I plus equals 2 is preferable to I is equal to I plus 2. In addition, for a complicated expression like YY val, okay, the assignment operator makes the code easier to understand since the reader doesn't have to check painstakingly that two long expressions are indeed the same, or to wonder why they're not. And an assignment operator may even help a compiler to produce efficient code. We have already seen that the assignment statement has the value and can occur in expressions. The most common example is while get car C so and so. The other assignment operators can also occur in expressions, although this is less frequent. In all such expressions, the type of the assignment expression is the type of the left operand, and the value is the value of the assignment after the assignment. Exercise 2.9. In a 2's complement number system, x ampersand equals to x minus 1 deletes the rightmost 1 bit in x. Explain why. Use this observation to write a faster version of bit counts. I like that as well. Conditional expressions. The statement if A is greater than B, Z is equal to A, else Z equals to B. Compute in Z the maximum of A and B. The conditional expression written in the ternary operator question mark colon provides an alternate way to write this in similar constructs in the expression 1, expression 2, expression 3. So you can say Z is equal to A is greater than B question mark A colon B. Yep. The expression 1 is evaluated first. If it's non-zero true, then the expression 2 is evaluated, and that is the value of the conditional expression. Otherwise, expression 3 is evaluated, and that is the value. Only one of expression 2 and expression 3 is evaluated. Thus, to set Z to the maximum of A and B, you can do this little expression here. It should be noted that the conditional expression is indeed an expression, and it can be used wherever any other expressions can be. If expression 2 and expression 3 are of different types, the type of the result is determined by the conversion rules discussed earlier in this chapter. For example, if f is a float and n is an int, then the expression n is greater than 0 question mark f colon n is of type float regardless of whether n is positive. Parentheses are not necessary around the first expression of the conditional expression since the precedence of colon equal is very low, just above assignment. They are advisable anyway, however, since they make the condition part of the expression easier to see. The conditional expression often leads to succinct code. For example, this loop prints n elements of an array, 10 per line, with each column separated by one blank, and with each line, including the last, terminated by a new line character. Makes sense. A new line is printed after every 10th element, and after nth, and after the nth. After all other elements are followed by one blank. This might look tricky, but it's more compact then the equivalent if else. Another good example is printf. You have %d items, %s. Yeah, because item is pluralized. I've used that a lot. So exercise 210, rewrite the function lower, which converts uppercase to lowercase with the conditional expression instead of if else. Not going to do that. Precedence and order of evaluation. Table 2.1 summarizes the rules for precedence and associativity of all operators, including those that have not yet discussed, that we have not yet discussed. Operators in the same line have the same precedence. Rows are in order of decreasing precedence. So for example, star, multiplication, division, modulo all have the same precedence, which is higher than that of binary plus and minus. The operator parentheses refers to function call. The operators arrow and dot are used to access members of structures. They will be covered in chapter 6 along with size of an object. Chapter 5 discusses star and direction through a pointer. And ampersand, address of an object. And chapter 3 discusses the comma operator. Note that the precedence of the bitwise operators ampersand, caret, and pipe falls below equals and not equals. This implies that bit testing expressions like x and mask is equal to 0 must be fully parenthesized to give proper results. C, like most languages, does not specify the order in which the operands of an operator are evaluated. The exceptions are ampersand, logical and, logical or, the ternary operator, and comma. For example, in a statement like x equal to f plus g, f may be evaluated before g or vice versa. Thus, if either f or g alters a variable on which the other depends, x can depend on the other order. Thus, if either f or g alters a variable on which the other depends, x can depend on the order of evaluation. Intermediate results can be stored in temporary variables to ensure a particular sequence. Similarly, the order in which function arguments are evaluated is not specified. So the statement printf ++ n power 2n can produce different results with different compilers depending on whether n is incremented before power is called or after. The solution, of course, is to write ++ n power. Yeah. Function calls, nested assignment statements, and increment and decrement operators cause side effects. Some variable is changed as a byproduct of the evaluation of an expression. In any expression involving side effects, there can be subtle dependencies on the order in which variables taking part in an expression are updated. One unhappy situation is typified by the statement AI is equal to I++. The question is whether the subscript is the old value of I or the new. It depends on the precedence. Compilers can interpret this in different ways and generate different answers depending on their interpretation. The standard intentionally leaves much such matters unspecified. When side effects assignment to variables takes place without an expression is left to the discretion of the compiler, since the best order depends strongly on machine architecture. The standard does specify that all side effects on arguments take effect before a function is called, but that would not help in the call to printf above. The moral is that writing code that depends on the order of evaluation is a bad programming practice in any language. Naturally, it is necessary to know what things to avoid, but if you don't know how they are done in various machines, you won't be tempted to take advantage of particular implementation. I think maybe if they specified these things more in the language, it wouldn't be an issue. the language could clearly just take an opinion on what the proper ordering of evaluation is, and not leave it up to the compiler or the architecture. I think that's part of the reason why C is just like a pain in the ass. Okay. There's just a precedent and associativity of operators table. Makes sense that assignment is so low. And that the subscript and function call and member access operators are so high. And then you got exponentials are not in an operator, so you can eliminate that, but parentheses obviously you can use those to force precedence, so they're the highest level. So please excuse, then multiplication, division, MD, and then Aunt Sally plus and minus. So, and then left to right associativity for everything. The ternary right to left associativity, I have no freaking clue how to read that stuff sometimes. The assignment being right to left makes sense. What's interesting is size of is not a function. I always view it as a function, but it's a statement in the language. So you can do like test size of .c. We'd say printf %d here, and then give it size of an int, and we'll just do 1 here. Yeah, it's effectively like the syntax is pretty much identical to a function, or is identical to a function. So, all right, cool. So it is 5 p.m. and there's a bunch of exercises I want to do as part of this chapter. They're all the bitwise ones. So what I'm going to do is I'm going to take a break here. I've been going for about close to 3 hours. So I'm going to take a break here, grab some lunch, and then I'm going to hop on for probably another hour this evening to implement some of the exercises. It should be pretty straightforward, bitwise operations. And then I'll do a commit, and we'll be done with chapter 2. So that's 2 chapters in 1 day. It's not bad progress. And that's about 54 pages. So pretty happy with the progress there. It also includes all the introduction and prefaces. So yeah, I'm happy with the progress. I want to try to do at least 50 pages a day. And then that'll leave us finishing within a week, because it's only like 200-ish, 225 pages. Not even. If you take out the reference manual and the appendices, is this? Yeah, it's 189 pages without the appendice. So we could probably finish this week if we don't do the appendices. Anyways, all right, I'm gonna hop off here. I'll be back in about probably an hour or so, maybe a little over an hour, to start on the bit totaling functions that we identified. Cool.